All right, welcome to this explainer. Today we're diving headfirst into what honestly feels like impossible magic, super tall skyscraper engineering. Seriously, if you've ever stood at the base of one of these modern megatowers, craned your neck all the way up, and felt a deep sense of awe mixed with just a tiny bit of anxiety, well, you are definitely not alone. So, we're going to break down the sheer, unbelievable structural genius that lets humanity build literal mountains out of glass and steel. Let's get right into it.
Okay, I want you to put your skeptic hat on for a second. Think about being a kid playing with wooden blocks. If you stack those blocks really, really high and then just give the top of the stack a tiny tap with your finger, what happens? Right? It falls over instantly. The center of gravity is just totally wrong. So, logically speaking, why on earth doesn't an 800-meter tall building just completely tip over the second the weather gets bad? How do we keep millions of tons of stuff perfectly upright when all of nature is actively trying to knock it down?
To really wrap our heads around the pure absurdity of the forces at play here, think about this. A super tall skyscraper can weigh as much as 100,000 elephants. That is a staggeringly huge amount of raw downward mass. But on the other side of that equation, you've got 100-mile-per-hour hurricane-force winds just slamming directly into the side of it. It's an all-out battle between the crushing weight of the building pushing down and the devastating sideways force of the wind pushing across.
So let's jump straight into round one of this fight, gravity versus the sand.
The skeptic in me says, before you can even think about building up, you have to build on something solid, right? But how do you build a megatower in a place like Dubai where there is literally zero bedrock near the surface, just loose beach sand? Well, this is where we channel our inner engineer. They use a brilliant concept called friction piles. Unlike a normal building that sits on a hard rock bottom, a skyscraper in Dubai uses hundreds of reinforced concrete poles driven deep down into the loose earth. The building doesn't actually sit on anything solid. It stays completely suspended, held in place purely by the sheer friction of the sand pressing against the sides of the poles. It is wild.
Let me walk you through how this works, because it's actually pretty simple. First, engineers drive these massive concrete poles super deep into that loose sand. Second, as the pole is jammed downward, it shoves the sand out of the way, which makes the earth around it naturally compress and pack incredibly tightly. And third, all that extreme compression creates massive shear friction. It grips the pole in place. The building isn't sinking because the earth itself is basically giving it a microscopic, high-pressure bear hug.
Once that foundation is locked in, we can finally look above ground. Think of a skyscraper kind of like a giant human body. To stay standing, it needs a really strong spine and a super wide stance. Engineers pull this off using what's called a buttressed core. Picture a hexagonal central hub made of ultra-high-strength concrete, shooting outward with three wings that act like giant stabilizing legs. This incredible shape makes sure the building won't twist or lean under all that insane stacked weight.
All right, moving on to round two, the war against the wind.
So we beat gravity, and we beat the sand. But now we're facing a much more dynamic, aggressive enemy. As any structural engineer will tell you, gravity is heavy, sure, but it's predictable. Wind? Wind is a fighter. It's actively trying to rip the building out of the sky. And its main weapon in this battle is a terrifying aerodynamic phenomenon called vortex shedding. When high-speed wind hits the flat, massive side of a skyscraper, it splits. And as it flows around the back, it creates these swirling eddies, or vortices. If those swirling gusts happen to sync up with the building's natural vibration frequency, boom, it creates this rhythmic, highly organized attack. Left unchecked, vortex shedding will literally shake a flat-surface building to pieces.
So, how do you defeat an invisible enemy that attacks in a rhythm? You use the confusion strategy. Architects fight back by designing buildings that intentionally break up the wind's flow. Take the Burj Khalifa, for example. By using stepped-backed architecture and tapering shapes, basically constantly changing the shape of the floors as the building gets higher, the wind gets totally confused. It can never lock into a rhythm or form an organized vortex at any single height.
And you know, sometimes the best defense is the simplest. Just softening or rounding the corners of a square building, instead of leaving them as sharp, harsh 90-degree angles, completely disrupts that aerodynamic flow. That one tiny architectural tweak alone can drop the sheer force of the wind by up to 20%. Seriously, a 20% reduction in stress on the whole skeleton of the building, just by smoothing out the corners.
Which brings us to round three, the skyscraper's iron heart.
Here's the thing we really need to understand. A skyscraper is not a static, unmoving object. To survive typhoons and massive wind gusts, the building actually has to be an active, moving machine. Buildings sway. They literally have to. If they were totally stiff, they'd just snap in half. But if they sway too much, the people working up top would honestly get seasick. So to fix this, engineers hide massive, secret counterweights near the top of the towers. It's called a tuned mass damper, or TMD, and the undisputed king of TMDs lives inside Taipei 101.
Get this. Hanging perfectly suspended right between the 87th and 92nd floors of Taipei 101 is a giant, gold-colored steel ball. And the weight of this thing is it's mind-boggling. 660 metric tons. Just picture a solid steel sphere that weighs as much as a small Navy ship, just quietly dangling above the clouds in the middle of a busy office building.
No way, right?
But that sphere is literally the beating heart of the building. It acts as a massive pendulum. It's rigged up to these super thick hydraulic cylinders that work like giant shock absorbers. The movement of the ball is brilliantly engineered to be timed slightly out of phase with the actual sway of the building itself. It is a completely active, dynamic defense system.
Let me paint a picture of exactly how that heartbeat eats the wind's kinetic energy. Say a huge typhoon hits. The wind slams into the building and shoves the top of the tower to the north. Well, at that exact millisecond, the massive steel ball's inertia makes it swing to the south. The crazy heavy weight of that ball pulling in the exact opposite direction perfectly cancels out the energy of the wind. It keeps millions of tons of steel and glass completely still.
Now, not every building has a giant gold sphere hanging out in the lobby. Some ultra-tall towers, like the Comcast Center over in Philly, use something called liquid dampers. These are essentially massive hidden swimming pools or slosh tanks way up at the top of the tower. When the building sways one way, hundreds of thousands of gallons of heavy water slosh the exact opposite way. It achieves the absolute exact same dampening effect to stabilize everything.
All right, bring it all together. Engineering is greater than gravity.
So, as we wrap up this explainer, I think the biggest takeaway is that staying upright at 800 meters in the sky isn't about being rigid, and it's sure as heck not just about pouring more concrete. It's about being incredibly smart. Humanity's ultimate defense against nature up there relies on three brilliant things: a strong structural spine using that buttressed core and friction piles, confusing the enemy wind with tapered architecture, and using those massive hidden counterweights to literally eat the kinetic energy of a storm.
We have pushed past 800 meters. We have effectively conquered the sand, the wind, and gravity itself. But looking at all of this, it leaves us with one incredibly provocative final thought. As our building materials get lighter and our dampening systems get smarter and smarter, how much higher can we actually go before physics says no? It really feels like the sky is no longer the limit. Thanks so much for joining me on this explainer, and hey, keep looking up.